So you'll see, I mean, if you want me to do that right now, I can. So I thought I'd put it at the end of the video so I can maybe bookmark it on YouTube.
So the shift is always first?
The horizontal shift is first, then horizontal dilation, then vertical shift, or vertical dilation, then vertical shift. So it's always that order, always. So, transformations. Horizontal shift to horizontal dilation, vertical So, and you should write down what you're doing, and like, if you have a problem like you had before, you should also be like, first I'm doing this, and second I'm doing, because it's not obvious. Like, I think some of you may have gone top, bottom, left, or I don't even know. So, I mean, I swear one person went like diagonal, 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 diagonal. So, but it's still like, it looks like that's what they labeled, but it does not look like what they did made sense anyway. So, which is not surprising if that's your methodology for approaching that problem. Let me do a transformation for an exponential function. And we'll do it sort of exactly like it appears on that, on the last test. Like, what if I have e to the, let's make it 2e to the negative x minus 2 plus 1. Okay, so first thing I'm going to do, number 1, parent function. What's the parent function?
E to the x.
E to the x, and I'm going to pick some points on that, and some nice points. So, like a really nice point on exponential functions is
0, 1.
yeah, 0, 1. That's a great point. Another nice point is 1e. So, right, I just put in 1, and e to the 1 is e. So e is very close to 3. It shouldn't scare you to write 1 comma e. So that's an exact number. This also has a horizontal asymptote at y equals 0. Yeah. What sort of things can affect the horizontal asymptote, by the way?
Shifts.
What kind of shift?
Vertical.
Vertical shifts. That's what will affect it, right? That is what will affect the horizontal asymptote. Vertical shifts. Not vertical dilations, not horizontal dilations, not horizontal shifts. And similarly, horizontal, now your horizontal dilation can actually affect your vertical asymptotes to some extent. So we'll see that in a second. But let's look at this. So now, 2, I'm going to rewrite this. And why am I going to rewrite this? Oh, I guess I had it. Yeah, I'll leave it like that. I wrote it like that. Let me actually write it like this really quickly, just to rewrite it as I had it. I meant to do that. So I'm going to pull out the negative 1, and then I'm going to have x minus 2, and then plus 2, right there. E to the x is my parent function. This is my argument. That's my what? My horizontal shift. So the reason you actually really want to do all of your transformations like this, don't.
Why is it plus 2? Should I be for the vertical?
Oh, plus 1. Sorry. I meant to write plus 1, and I just wrote a bunch of 2s, so I was like, one more 2. So I love 2.
Are there classes x plus 2 or?
I'm saying this, like, let's pretend this is that's what I meant to write, and then I went ahead and went to the next step.
Okay,
So-
it's negative x plus 2, is that what it says?
Yes, that's the exponent. Negative x plus 2 is the exponent. So I pull out the negative 1 from both of them. And then that's x negative times x minus 2. This, because we're going to be doing trig functions soon too, and the only way to deal with them is to learn to deal with it like this. So otherwise we'll just get it wrong every time. Now the first thing I do here is horizontal shift, right? To where? Horizontal shift, right 2. And write this. Right 2. And let's look at how easy this is to deal with. Here we have the point 0, 1. Where does that point move to? 2, 1. And now I have the point 1e. Where does that move to? 3e. So I'm just grabbing onto those points and following where they go. All right. Now, since I have this in this sort of form and this negative right here, I no longer flip about the y-axis. I flip about that point. I flip about the point that I shifted the whole function over to. So that becomes my new axis of, I guess my axis of symmetry, my axis of rotation. Probably vector. So this point is fixed right here, right? It's still 2, 1. But now what happens? That point moves over. It was at 3e. Now it's at. It was 1 away from here. Now it'll be 1 away from here the other way. So it'll be at 1, e. Do we understand why that is and what happened there? So really I'm just looking at the relationship between points around this axis. So this point is sitting on it, so it stays fixed. This point was 1 away. It'll be 1 away when I flip it, but in the opposite direction.
So it was flipped because of the negative that's outside?
Yeah.
Okay.
So exactly. Horizontal dilation. Flips about x equal. It doesn't do anything else there. That's all it does. I guess I could continue right here. Four. What's the next thing I do? Vertical dilation, exactly. So I just look over here, and now this one tends to upset people. But the thing to realize is all I've been doing up to this point is operations on the x coordinates. Now for the rest of it is all I'm going to be doing is operations on the y coordinates.
I think you had to multiply for some reason for the horizontal dilation. I think you had to multiply with 2 x. Oh, wait.
There's only a 1 here, it's a negative 1. So everything up here is stuff that affects the horizontal. Stuff outside of that is affecting the vertical. Because your parent function is e to the x, so e to the stuff is the stuff affecting your horizontal movement, right? Not the, now this affects your vertical, right? Because you think of like e to the x is giving me some y value, and this is doubling that y value, right? And so now I go over here and I look at my x values. My x values at this point are all fixed. They're all fixed. So the only thing that's going to change is y values. And so I have a point at 2, 1. Where does that point go? 2, 2. Because I just double the 1. So that 2, 1 went to 2, 2. And where does the 1e go?
1, 2.
Exactly. That's all there is to it.
Yeah, that's what I was talking about here. So I thought it was the same thing when you multiply by -1.
Yes. I multiplied by -1. So, like, what's happened though is this translation in some sense has moved the y-axis so that the y-axis lives here. Like, I mean, it doesn't literally, the y-axis is still there, but it is actually the same phenomenon in principle. So it's better to sort of remember what happens to it symmetrically. Like the only thing you're doing is flipping. Now the other thing you can do is just put in the points and see if they match up, right? So we want to see it like put in 1 and see what you get. Like forget these two, and if I put in 1 at this point, right, I can write right here, this is equivalent to e to the negative x minus 2, and over here it's going to be, oh sorry, this is just equivalent to x minus 2. And then this is equivalent to e to the negative x minus 2, right? Because here I just moved it over. Now here I flip it, put in 1. What do I get? 1 minus 2 is, and negative 1 is, and there I get 1e. You can do that. You can check your values, make sure they make sense. So that was like a lot of the, like on the back page of the last exam, the last problem, most people got almost everything right, and then you graphed something that didn't even have the points that you put on there, and I was just like, whatever. So I don't even know what to say to that. But you can put in the points, and just remember those are points, and you're putting them in. So right here, I mean the graph is only like hardly any, I mean of the 8 things it was like half a point, so and the last thing to do, okay, let me write out what this was too. This is 2e to the negative x plus 2, and this is a vertical dilation. You can write stretch or shrink if you like that word better. Vertical dilation by 2. Someone was telling me that they think this word fell out of favor because of gynecologist. I kid you not. That was so because of people visiting gynecologists, because dilation has a secondary meaning in gynecological science, and that upset people to hear that word in math class. So there's like a paper somewhere, Journal of Education. So I don't know. I'm not sure how apocryphal that story is. It might be totally false. It might also be. I mean, there's that great education study about school uniforms improving grades, and that has never been replicated. But if you look at the study, they did it with like 11 people, and they did it like they didn't actually look at the grades. They just sent out a bunch of propaganda, and they asked people how they felt about their school before uniforms. Then they sent them a bunch of stuff telling them that school uniforms make your schools better. And then they asked them how they felt about it afterwards. And that was that whole study that got like countless schools to switch to school uniforms. But on the flip side, it made a lot of money for people who were making school uniforms. So, last thing to do is move everything up 1. Now when I say move everything up 1, what does that include? The asymptote, yeah. The asymptote is now, AJ is now y equals 1. Keep in mind the horizontal asymptotes are y equals, the vertical asymptotes are x equals. And now we just moved the points up, right? That was at 2, 2, so now it's at 2, 3, yeah, 2, 3. And the other point was at 1, 2e, and now it's at Yeah, it's about 7. 1, 2e plus 1 is just what I'd write. Just write it like that. It's close to 7. And there you go. Now, this isn't an asymptote here, it's just going up very fast. There's no vertical asymptote for this. So that's a nice example of graphing. They all follow pretty much this procedure. Do you want me to do one with log?
Yeah.
This is a good one too because people will make themselves really upset because they'll forget log properties. Because log properties are going to make this easy. Because I can give you something that at the outset looks quite daunting to graph, right? So everyone's got this, I can erase this. This board is the easiest thing to see and work on. Let's do g of x is the ln of, I don't know, let's make this. So that seems like it's going to be quite daunting, right? Except we can just start rewriting it. Like, what's another way to write the third root? And now, what property can I use? Yeah, so all that ever was a coefficient, and now you know how to deal with it. And also, I probably want to factor this negative out, right? And negative 2, and rewrite this as x plus 2. And you have to do that. So the other thing is you have to do that because you won't have the right shift otherwise. You'll have the wrong shift. This is the other reason that, because almost all of the problems she's had have just been negative x plus stuff. And so you can sort of do the shift and then do a reflection about the y-axis, and that works. But it only works in the case where this coefficient is 1. Otherwise, it just fails in general.
So that would be basically the opposite, right? Before we pulled out a negative. Now
we're pulling out a negative, but we put on negative 2. We want to pull out whatever. If there's a coefficient in front of the x, we're going to pull out exactly what that coefficient is of every term, whatever that coefficient is. If it was 1/3, I would pull out 1/3 from both terms. Now keep in mind, this could end up with something that doesn't look super nice, right? Like if I had 2/3 x plus pi, then I now have 2/3 times x plus 3 pi over 2. Right? So that could happen. That is a possibility. We've got more simplifications that we could make if we really want to. So this just sort of depends. Like the problem with logs and let's just leave it like this though. This is going to be because right, I could make this ln2 times the plus negative x plus 2. So logs and exponentials have this property that you can, in general, get rid of leading coefficients by using exponential properties. Like they can always, or get rid of, leading coefficients for the x. Like horizontal dilations are always equivalent to vertical shifts. So that's just a property of them. So let's start with the parent function. Parent function. And the parent function of this is ln of x. So it's ln x. And let's pick some nice points. How about this one? What point is that? 1, 0, yeah. And then we could pick another nice point out here, and I'm going to call this point e, comma, 1. The ln of e is 1, right? Because it's just log base e of e. That's all ln means. I could have picked e squared or e cubed if you like those numbers much better. Now, what's the first thing I do now? Horizontal shift. Yeah. 2 to the left. So this point was at, oh, there's a vertical asymptote which I should make note of, right? So vertical asymptote at y equals 0, x equals 0. So now I move this 2 to the left. My vertical asymptote is now x equals -2, right? And my points, I move them both 2 to the left, right? This was at 1, 0, so now it's at -1, 0, right? And this other point is at e, comma 1, so it's going to be e minus 2, comma 1. So it's like right there. Now what do I do? Horizontal dilation, and then 2. Horizontal dilation by -2. Notice this is going to flip. This is going to flip everything about. Well, let's look. What's going to happen? This moved over here, and when I flip all of these points, they're going to come to the other side of this, right?
Is
So-
the other side of the asymptote or the other side of the?
The other side of the other side of the asymptote.
So why in the other problem it reflected over like that?
It's actually reflecting over the line x equals -2, which is where the asymptote is. Does that make sense? It's reflecting over the line of translation.
So if it's affecting the x, it would affect the y.
Yeah, it's going to be a y flip, and it's going to be about this line. It happens that it's the asymptote. I mean, it turns out it's always going to be the asymptote for the log. Yeah, for anything that has an asymptote that's at 0 naturally. It's going to be the asymptote that will then reflect over. Does that make sense? It just moved, like, this x plus 2 is telling me that I'm reflecting over the line x equals -2, which happens to also be the asymptote. So in a way, it's kind of convenient here. So this point that was at -1, 0 is now going to be at -3, 0. And this point that was at e minus 2, 1, oh, that's going to be a real nightmare. Let's see. It's still going to be 1, and it was about 0.7-ish from this point. So it is, I mean, I can actually give you the, it's going to be -3 plus e minus 2, right? Yeah. So it's going to be negative 5 plus e, and that makes sense. So that's painful. We could also just put this point here. I'm going to call this point, I'm going to call this value whatever. So that, say close to 1 there. And so it's going to be close to 1 away. So it's going to be negative 4-ish, approximately negative 4, 1. As opposed to making it some terrible number. I mean, really, let's see. What number would give me? I'll put 1. Let me write out what this is. So this is the I of x plus 2. This is the n of negative 2 times x plus 2. Where does that equal 1? We can figure that out exactly, I guess. X plus 2 equals 1. So that says e negative 2x minus 4. So e plus 4 negative 2x. Oh yeah, this is what it should have been. If we want it exactly, it is e plus 4 over negative 2. So we could have solved for it exactly. I just said, like, it's equal to 1 over here. It's got to be equal to 1 over here. This is the equation we're dealing with right now. I got the point back for all that it's worth. I mean, I just did that too. So we have the exact point, so you know how to solve for it if you really want it. And 2, because the x values don't change after this, right? Everything I do at this point is going to change on the y values. So once I have it, it's going to stay there.
So on the test, we won't need to find the exact.
You pick nice points. Probably they won't be this horrible. So, I mean, that's not that bad, right? E plus 4 over negative 2 is not like the worst number imaginable. But you could also approximate it at one point and say this is really close to this. Because really when you do those flips, you're preserving relative distances, right? Oh, and that's good. It's good that I actually did that because I made a slight mistake in my estimation, right? Because this is e plus 4 over negative 2, which actually makes this only about 1/2 away, right? Instead of about 1 away. So it's a little closer than I had initially put it. E plus 4 over 1. So it looks like that. So it's just going up a little bit faster. All right, we've got 2 things left to do. What are they? Vertical dilation. And we've got these beautiful points of negative 3 to 0. Negative 3 to 0, that stays there because 1/3 times 0 is 1/3. The other one becomes what? The other one is, I'm going to just put it over here, it's e plus 4 over negative 2, or do like minus e minus 4 over 2, comma what? 1/3. Just 1 times 1/3. So that flattened it out.
When you do the vertical dilation, so it's multiplied by y, when you do the horizontal.
You're dividing it. I mean, we sort of saw exactly why you did that, right? When I solved for it.
Yeah.
Because what happens is you end up dividing by it if you solve for the x, if you look at the y. But there's another way to think about that, and it's simply this. It's like you look over here at, say, this function. This function gives you a half circle. 1 minus x squared gives you the top half of the circle. and its domain is from -1 to 1. And we would call this f of x, right? So now what happens if I do f of 2x? Well, its domain is not -1 to 1 anymore. It is now -1/2 to 1/2, and it's no longer a half circle, it's a half oval. So, well, why is that? It's because 2 times -1/2 is -1, right? It ran through its domain sort of twice as fast. That's what happens here. And that results in a horizontal contraction when this is bigger than 1. It's running through its domain faster. So it's picking up all of those numbers more quickly. And if it's less than 1, it gives me an expansion because it's running through all those numbers more slowly. Does everyone sort of sees that? I mean, there's more than one way to understand each of these particular things. And then the last thing I do is vertical shift. And that is a vertical shift of everything by 1. So this comes to 3, 1, and what was it? -e minus 4 over 2, comma 4/3. Yes.
So when you do the horizontal dilation at -2, that means we divided the x values by -2, right?
Yes, exactly.
So how do we get from -1 to -3? Like, see, instead of 2, it was -1, 0.
Oh, maybe I did make a mistake.
Let's,
Actually, that shouldn't, this is, I think, going to work out because, let's do this though. We can find out exactly what it is though, because we can do this, right?
yeah,
No,
I
it's not.
remember negative terms and
Oh, yeah, you're right. Thank you for doing that too. So, because I raised e to both sides, you're correct. It should be, in fact, this is -1/2 minus 2, it should be -2.5, and you were correct. So thank you for checking me there. So it should be closer to this too. So that's 2 capital error, -2.5, 0. Excellent observation. -2.5. -2.5. So, and keep in mind, we can just solve for those x values if we need them. So this does sort of, and you're right. So like, you could have seen that really easily too, simply by looking right anywhere.